Okay, so we're still talking about external flows, and so to follow up from last time, we had this discussion on lift and drag, which are really two sides of the same coin, I guess, in some respects, in that they are both about forces induced by either pressures or viscous shear, and it just depends on which orientation we're looking at. Lift being perpendicular to the direction of the kind of far field airflow, which would be horizontal in this case. Presumably in this case there's no airflow, but the plane is moving relative to the static air. Let's assume it's static, and based on that you get lift vertically upwards and you get drag against the front edge of the wing. So you have both acting in different magnitudes. And so all this is, I just looked up last night, stalling airfoils. And so we looked at it a little bit last time. We had this Cambridge University wind tunnel movie, it looks like it's from 50 years ago, of an airfoil in a wind tunnel with smoke trails around it, looking at changing the attitude of the airfoil relative to the direction of the air coming over it, and looking at how the vortices change on the backwards. And that's exactly what this is. This is looking at trying to stall the plane, I guess, reduce the velocity and also change the angle of attack so that all of a sudden there's not enough lift to be able to hold the plane up in the air. And so it's quite an interesting way to do it. This is just an impromptu way of putting pieces of wool or something, like these telltales. Not very many, are there? That's fine. These telltales on the wing, and to see exactly what they do in terms of the direction of flow across the wing. Same kind of telltales that you'd have on a sail on a sailboat. So I guess I've turned this off. It's probably actually been playing over me actually, because I thought there was a narrative on this. And so really just to look at the idea of lift and, to make the point that lift and drag are part and parcel of the same thing. So nothing particularly spectacular in this, but just to get us off in the right way in looking at these behaviors. Okay? Get out of this and go back to this. So the material today is still to look at external flows, and the characteristics of external flows aren't so different from what we talked about in terms of dimensional analysis. In dimensional analysis, I guess we made the case that first of all we want to have what we call geometric similitude. And so for a airfoil, if we had it, then geometric similitude between a model and a prototype might be that the length to height ratios were the same between both components. So there's no difference between, so a scale model is a scale model in every sense of the word. If we wanted to look at flows, then we had to look at kinematic similitude. I won't write it out. And that for us was basically that the flow patterns around the prototype and the model were identical to each other. And that's important to us because we know from what we talked about yesterday, on Monday, not yesterday, for flow around in pipes or around structures, that if you look at the behavior of these systems, then at least for flow around an external flow, typically it would look, we'll find out today, it may look something like this. And the important part is that the laminar regime and the turbulent regime divided through by some, for pipe flow we know this is something like 2100. For these flows it might be something like 10 to the 1. It doesn't really matter what the number is. But in this region here, the drag coefficient is proportional to some constant over Reynolds number, in the fact that these are both log scales, and in this part here the drag coefficient is constant. So this is some constant. We'll find out today that it might be 24 for spheres. Doesn't really matter. And so kinematic similitude means that if you look at flow around a sphere, then in laminar flow, that flow would be hugging the sphere and coming out on the back end. And the streak lines would look like this. But for increasingly higher flow velocities, then it would be this turbulent wake that would exist behind it, with these vortices shed off at periodic intervals that would go downstream. So physically the flow systems don't look the same unless you're working at the same Reynolds number. And the same Reynolds number they would. And the third part is that dynamic similitude requires that typically the Euler numbers are the same. And so that's apparent here, because if you look at this is exactly an Euler number, right? This coefficient of drag is the same as a pressure divided by rho v squared. Rho v squared. This here is a force divided by an area, which is a pressure, and there's a factor of 2 in the calculation. And so it's the same calculations that we've done before, so there's no difference between looking at model behaviors and looking at what we're looking at now. It's exactly the same behavior if we're looking at behavior for pipe flow. This would be multiplied by this. These would be equivalent if this was the case, with this geometry in there. But it's just a magnitude of a force that's applied here. So the 3 same portions. Define exactly what the geometry is, one-to-one relationship between the dimensions of something. Make sure the flow regime looks like the same flow regime in both cases. And if that's the case, then if you measure the forces on a model, you can use those to calculate what the equivalent forces would on the prototype. And those forces would be either the drag force that you apply or the lift force that you can use to kind of scale between the two systems. So that's really what we're attempting to do here. So with that in mind, I'm going to kind of go off script from this and do something else, do something that I told you I'd never do, but I'll tell you what that is when we get to it a little later on in class. And just to recap from what we talked about. Lift and drag are really very similar to each other. All that's different between lift and drag is that lift is perpendicular to the flow, and drag is the force applied in line to it. So that's the first thing that we might be aware of. We know that we can calculate both of these components, and that's the first thing we'll do. Oops, sorry. Lift, whoops. We can do this by realizing that there are 2 components. They are due to, and there's a diagram in your notes that basically makes this point. Imagine one of these fancy helmets that someone wears to make you go faster. Is if you look at the flow around one of these, you could imagine that there are 2 attributes. One is that there's drag along this portion here, and there's stagnation pressures on the front. So there's pressure drag, and there is viscous drag. So this shear stress here is due to viscosity, and this is due to the magnitude of pressure that's applied on this face. So clearly there's two components that are contributing to the force that you have to apply to overcome this, and we need to realize that that's the case. We should realize also that in this regime here, this is dominated by viscous drag, and in this regime here, this is dominated by pressure at higher velocities. So these, not only do they change based on kind of the aspect, if you like, of the structure relative to the airflow. So this is the airflow direction here, and typically this velocity here is used is the far field velocity, because that's the one you could measure. So in other words, if it's a plane flying in a static air, then it would be the velocity of the plane, basically. And it depends on the aspect of this and also the flow regime that you find yourself in. And so those are maybe the key messages from this. So what I wanted to do today is do two things. I wanted to go through, the first thing is calculate the magnitudes of lift or drag from the mechanism that we kind of introduced last time. The second one is calculate from we talked about pressure and shear stresses contributing to this. So want to also calculate lift and drag numerically. And I'll re-invoke a past video for that. And then talk about the final calculation sequence. In terms of actually why, I suppose. Why do we interested to do this? And so, I mean, you can cut to the chase. It's probably worthwhile just, I mean, it's very simple as to why you might want to do it. So we might want to have, for instance, a static object. So in other words, have a static object and calculate forces applied. So I'm sure we'll do an example next time on a water tower with air going past it. Looks like a tree, I know. And so what are the forces that are applied in terms of the moments, for instance, applied on this to be able to design this. And the other option would be to calculate freefall velocities. And so that would be, for instance, if you're parachuting, and this would just be that the sum of forces in this system are equal to 0. And if you do this, then you can calculate the velocity. So you know that there's a weight acting downwards, there's a drag force acting upwards. If you equate those, and you can define those in terms of a coefficient of drag or a force that's applied by just rearranging this, then it shouldn't come as any surprise that we can calculate from this the velocity, the terminal velocity as you come with the parachute or as you free fall in space. So those are the things you do, yeah.
What is that word number 3?
Calculation sequence, why? Sequence, yeah. Maybe that's better. So that's what we might try today. So we'll do. So I guess we've kind of done this third one, and that'll become more apparent when we do some things on Friday. But let's deal with each of these first two. The first one follows exactly what we've talked about before in terms of this equation, and that lift is defined relative to pressure lift and shear lift. And so we can look at each of these in terms of the, well, let's go back to the previous expression just to make sure that. So we can define drag and lift in terms of just by integrating the forces. We talked about it last time in defining exactly what the geometry was. So a portion of a surface has a length to it, which has an area. And if you look at the shear stress that's applied on this, or the normal pressure applied over some length dA, we can look at resolving those components normal and in the x direction from the values which are normal and parallel to that surface. So what we need to do is find the x and the y direction components, because those are the directions in which we'd like to resolve the forces. And if we do that, we come up with a relatively straightforward expression where the components of the pressures are just integrated over length of the contour and have an angle. The angle in this case is measured with 0 in this direction. This would be theta 0, this would be theta 90, 180, etc. And they give the correct orientations of these forces. And if we use that, then what we can do is, if we know, for instance, exactly what the forces are that are applied on a structure, either by measuring them or by coming up with some simple equation for them. This comes actually out of boundary layer theory, which we don't need to talk about yet, but imagine that we can get the magnitude of what the shear stress is as we go across here. And this would give us a shear stress which is equal to this magnitude here as a function of x measured relative to the origin here. And so if we want to calculate what the magnitude of the lift would be, it's pretty straightforward to be able to do that, because just from the symmetry of this thing, you'd imagine that the pressures acting on this structure on the top would be exactly the same top and bottom, and by cancelling out, the magnitudes of the lift as a function of this would just be as given here. No shear stress in this, because the shear stress would have to be acting on this. And actually, if you think about the shear stresses, if you blew up a portion of this and made it much larger, so if you made it thicker like this, the flow is coming in here and splitting below and above, the shear stresses resulting from this would also directly cancel out. And they'd be trivial because it's such a small area. So in other words, it's a finite shear stress, it's a tiny area, so they'd be small, but also by virtue of the fact that it's symmetric, they'd be acting, they'd cancel out as you do the integrations. But if you look at the lift from the pressures that are defined across here, you can imagine that the pressures acting across here are also integrated along the length of it. And if you look at P, is it cosine theta? Cosine 0 is equal to 1, and cosine 180 is equal to minus 1, or the other way around, I guess, top and bottom. That gives you the magnitudes of this that give you just the sign convention that's here. And as a function of the fact that the pressures top and bottom would be symmetric, in this case they're 0, so they cancel out anyway, so there's 0 lift that's applied in this case. So it's a simple calculation to do that. If you look at the magnitudes of the shear stresses which are applied, given by this expression here, then the drag that you'd get would also be modulated by the appropriate cosines, I think in this particular case on here, to give you the magnitudes of these, which are additive. And you could just by inspection see that the shear stresses that are applied on this boundary would be the mirror image of each other on the top and bottom, and would be additive in terms of the integration. So the integration that we're looking at really is actually just the area that's under this curve. It's the area under this curve on the top, the area under this curve on the bottom, and written mathematically, it's merely this magnitude here. And so if we calculated exactly what those are, since they're additive, then it's just equal, and they're symmetric above the top and the bottom, then it'd just be equal to twice the magnitude integrated on the top by solution. So the drag magnitude would just be given by whatever the magnitudes are of these forces here. If you turn the plate pardon me, on its side and want to look at the magnitudes of the drag, then again you have these two components which would give it. This is the stagnation that occurs here, and the flow is both top and bottom. This is the pressure distribution that you have here. You could imagine, I suppose, that there would be a shear stress on the top and bottom parts of this plate, but if the plate has really zero thickness, then the magnitudes of those would be trivial. And so the only parts that we might want to worry about are the magnitudes of the pressure acting in this direction and the pressure on the backside, which in this case, if it really is a pressure which is in tension, negative magnitude, then these would also be additive as well. And so I think if you look at the magnitudes of these pressures, this is the calculation for the shear stress distribution, which is this magnitude here, substituted into here, which is the same as this evaluation here. The integration is along the length of this between 0 and 4 feet. And so if you do that integration, that's exactly what this is. This is the magnitude of tau. This is the fact that it's top and bottom. This is between the front end of the plate and the back end of the plate. And if you substitute those limits into it, you end up with a drag force, which is some magnitude. If you look at the lift, as we said earlier, it has to be 0 because they're symmetric to each other. And if you look at the drag by putting it on its side here, then this is the magnitude of the pressure, on the front. This is the magnitude of the pressure on the back. The integration is between, I guess this would be -2 and +2 in terms of the y coordinate. It's y squared, so it's going to be a symmetric distribution, this is just the equation of this, and this is just a constant over the back. And so if you look at the magnitude of drag just due to pressure drag, then this is the portion that's on the front, -2 to +2. This is the portion on the back, which is just a constant, which is integrated between this. So in other words, the integration of this times 4 feet, which is really just what this integration would give you, gives you a net drag force of 55.6 pounds. And so the mechanism of doing this is merely to be able to sum up the magnitudes. So if you actually look at what this integral would be, the integral actually is just the area that's completely under this curve. This one for the force acting here, and this one again for the force that is acting here. So if you take this whole area under the curve on the top and the whole area on the curve behind it, which is a vacuum, if you like, or a reduced pressure, then you add those together, and physically the integral is that. So it's perhaps useful to be able to define that. So this is the ability to do that. We mentioned last time that sometimes this isn't so useful because obviously you need to have an equation that gives you the magnitude of the pressure and the shear stresses, and they don't always exist. So it's a little bit contrived in some respects to do that. The other way to do this, which is the thing I never said I'd do to you, but I'm going to do to you, is that you can calculate it numerically. And what I said I'd never do, I think I remember telling you that my son took a class in engineering mechanics at Penn State, and the professor came to class, put on a video, and then sat in the class while the people watched this. And that's exactly what I'm going to do today for a small portion of this, merely because I don't have boot camp on my machine in this particular piece of software. And so I'm going to shut up in a minute. But what you could do is the things that we've just done with these expressions, you can also do numerically. And so for those of you, I don't know what the makeup of this class is, for all 1, 2, 3, 4, 5, 6, 7, 8, 9 of you, what programs you're in, but certainly if you're in petroleum engineer, you'll use digital simulators to look at single-phase transport and multi-phase transport in porous media. You'll do the same if you're an environmental systems engineer. Mining engineers look at ventilation problems. The processes of solving these problems are very similar. And so since I don't have this on my computer anymore, I'm going to play this, and I'm going to shut up maybe for 10 minutes, and we can maybe watch this, and I'll come back to it. I think it's self-explanatory as we go through this. We don't want to activate Windows now. Okay, so what I wanted to do was to make the point of what we've said before about this example that we ran last time. And if you remember, this example was of basically an airfoil that we had put in a wind flow. And I think I can't, I'm pretty sure I can't write on this. Yeah, I can't write on this. So, yeah. I can go have coffee. I could talk over it, but I won't. Yeah, okay, so this is an airfoil. We made the point last time that this is a model called a finite element model. It divides the whole body up into a whole series of little triangles. And for each of these triangles, it basically solves, you could think of each of these triangles as basically a Reynolds transport theorem domain, a free body domain, in which we're solving for conservation of momentum in x, in y, and mass in equals mass flow out, conservation of mass. So we have 3 equations for each of these elements. We change that so that we have 3 equations for each of these nodes in the system, and in each of these nodes we solve algebraically for velocity in the x direction, velocity in the y direction, and the fluid pressure at that point. So 3 equations for each node, 3 variables, so we can solve them. We define some boundary conditions. The boundary conditions we had for this was that the velocity is coming in at 1 meter a second on the upstream far field boundary. The velocity along the top boundaries reach 1 meter a second. So in other words, it's just moving this flow down through the system. And we had a pressure boundary here of atmospheric pressure, 0 gauge pressure on the downstream system. We prescribed some fluid properties for this, so a density and a viscosity. And we go ahead and we try and solve it for the magnitudes of the conditions that we have that represent that behavior. And so for the flow system, we have a density of 1, which is pretty close to a density of air. We have a viscosity, so this is what we called mu before, dynamic viscosity. And we choose a whole bunch of different viscosities. I think we changed them between 100 to 10 to the minus 3. I stopped at 10 to the minus 3 because it crashes after that, because 10 to the minus 3 is a very big Reynolds number, so we'll calculate the Reynolds numbers, and it doesn't work very well at largest Reynolds numbers. And so what we can do is we can run it to be able to solve for the system. The other boundary conditions we didn't mention is that on this boundary, we put a 0 velocity boundary. So basically a sticky boundary condition. It's called a no-slip boundary condition, which means that any air particle that hits this wall actually is stuck there and goes at 0 velocity. But as you get further away from this airfoil, the velocity increases until it gets back to the ambient conditions further away. So that's what we're going to run it for. These are the conditions. So I ran it for viscosities of 100, 10, 1, 0.1, 0.2, 0.01, 0.001 viscosity. You'll remember that the viscosity of water is about 10 to the minus 3 Pascal seconds. These are Pascal seconds. So this is the viscosity of water. This would be the velocity of masses, I suppose, right? Something much more viscous. The viscosity of air is about 10 to the minus 5. And so I can't use it here because it crashes, but it doesn't matter, because any of these, for instance, will give us different Reynolds numbers. Yeah. The velocity is the same in the system all the time, the density of the fluid is the same, but we're going to run it for different changes in the viscosity. And so if we run it, it runs relatively quickly. famous last words, of course. If you look down here, this is the viscosity. It did it for 100, it's doing it for 10, it's doing it for 1, it's solving it for 0.1, 0.01, and 1,000th. And so it should, I think it's stopping still. I have a hard time doing it for 1,000th. If you look up here, it's done it for 6 examples. This is the plot for the flow, the stream field. So each one of these arrows is 1 meter per second. These lines are just streak lines which show you the separation of flow as it goes downstream. And what you can do, what I'll ask you to do, is to calculate what the Reynolds numbers are for these. Tell me what the Reynolds numbers are. If we go to, so what, if I can keep these on the same thing here. So right now you see that this is when the magnitude of the viscosity is the highest, then since Reynolds number is velocity, which is 1, density, which is 1, times length scale. You didn't see the length scale, well you do see the length scale. This is 1 meter along here. The airfoil is about 1 meter. So velocity, density, and length, the product of those is about 1. And it's divided by the viscosity. So the Reynolds number for this is 10 to the minus 2. Right? So this one is 10 to the minus 2. So very low Reynolds number. You see that the flow exactly hugs this thing. There's no separation back here. If we, for instance, go in and we, I guess that's how we'll do that. So post-processing, if we do this, and we draw a cross-section which goes from the center of the airfoil, which is 0, 0, to the top, which is x, okay, that's right. And we do it for the velocity field. And so this is just the absolute, so it would be Vx squared plus Vy squared square root. So the absolute magnitude of the velocity that crosses that little component. This is the velocity field that we have. And so if you look at, I'm trying to get this out of the way. So this is the cross section. So we're looking at the velocities across this. You can see this. This is the case of the smallest Reynolds number, 10 to the minus 2. And you see the velocity is 1 meter a second here. As you get closer in, it goes to 0, and it goes relatively smoothly. If we look at it exactly on this, we can know exactly what these are. So this is exactly the same plot. This one here, I'm guessing, is the very small Reynolds number, so 10 to the minus 2. We did it for viscosities of 100, 10, 1, 0.1, 0.01, 10 to the minus 2, and 10 to the minus 3. So 6 of them, there should be 6 curves. And so individually, those curves should be for Reynolds numbers of 10 to the minus 2, 10 to the minus 1, 1, 10, 100, and 1,000, right? And so these would be the low Reynolds number curves. And you see they just smoothly grade into this background velocity, which I'm not sure why it's 1.6. It should be 1 close to the boundary. And as you look at the higher Reynolds number, I'd imagine this is the highest Reynolds number. It changes from 0 to the background very quickly, close to the airfoil in this particular case, and then it's relatively constant as it goes far away from this. And so we made the point before, it's probably easier to see this if you look at these figures here. Let's get rid of this. Is if you look at the magnitudes of the flow field, in this particular case, this is the flow field for the highest viscosity, which is the lowest Reynolds numbers.
So we looked at the velocities, and they go to 1.6 as you get to this boundary. The reason for this is because it's kind of confined flow. It's like flow in a box. So you can imagine this is a box. So now all the flow that has to go past this airfoil is squeezed into a cross-sectional area which is less than its full height. It's 1 all along here, but has to speed up here because it's constricted. So that's the reason it's 1.6.
Reynolds number of 100. And you see that this flow field nicely hugs the back of this and then just goes off linearly. We'd expect the resulting drag force from that to be mainly viscous. If we look at the value when we look at the highest flow Reynolds number. So this would be 10 to the 3, Reynolds number of 1,000. You see you get this separation at the back and this wake all coming in. And so the net result of this is that you have different flow fields, and therefore if you do the calculation to figure out exactly what we did by hand to calculate what the influences of pressure and shear stress are on the drag force, you'd end up with different magnitudes. So what we can also do with this is with these different magnitudes we can calculate what the drag components are. And so what we can also do, it's not so obvious to you maybe, but if we want to calculate the magnitude of the total force per area in the x component. So x is horizontally, and so this would be, since our flow velocity is horizontal, this would be drag, this would be lift, right, total force. And the total force would be the sum of all the forces acting due to both pressure forces and viscous forces. So what we could do is we could look at what those forces are for each of these Reynolds numbers. And so for the highest flow viscosity, if we look at the magnitude of the lowest Reynolds number, the magnitude of this force is 1,300 newtons per meter. So I'm not sure if I can do this very easily. See if I can do it. So let's do this. So for instance, what we could do is we could plot, in this particular case, what do you want to plot? We could plot CD, for instance. It's not so easy to do, but you're going to help me do this. CD is equal to the drag force divided by a half rho v squared. Actually, it is easy to do, right, in this particular case, times area. So in this particular case, what are the magnitudes of those? Half is a half, the density is 1, the velocity is always 1 coming into the left-hand side, so 1 squared is 1, and the area is going to be equal to our length of the airfoil multiplied by 1 meter length into the board, which would also be 1 as well, and it's just divided by drag. So in other words, it's equal to 2d. So let's not worry about that. Let's plot CD over 2, which is equal to this. No, 2CD.
No, CD over 2, actually. But that's fine.
Just makes life easier for us.
Come on in.
So we plot drag force against Reynolds number. And if we do that, we have, what were our magnitudes that we had? We had Reynolds number, it was 100, viscosity of 100. So the Reynolds number is equal to 10 to the minus 2, 10 to the minus 1, 10 to the 0. I guess we might not want to do all of these. 1, 2, and 3 on a log scale. And we're just going to plot D. We know that it starts off, I've kind of screwed up my axis, but let's do the axis over here. This is what? This is 10 to the 3, 10 to the 2, 10 to the 1. Am I going to get 10 to the 0? I may run out of space, but you'll get the idea from what we're trying to do. And we'll go back to it. So for the case when we were flowing at the smallest Reynolds number, the total force applied on this was equal to 1,300 newtons. So you see you took me up on my offer. So 1,300 newtons is just more than 1,000, so it's up here somewhere. Go here. We don't necessarily want to do all of them. What happens if we reduce the flow by a factor of 10? Calculate the force that's applied.
Viscosity.
132. So that's kind of interesting, right? It scales as a function of the viscosity directly. So here, this is 100, so it's going to be something like this. We do it again, we come back another order of magnitude. So this is a Reynolds number of 1, I think. And it's equal to 13.2. That's kind of interesting. So we see that in this zone, so this is 10 to the 1, which is the 10. So it's about here. So these are actually joined by a straight line. And this is our drag total. Or it's actually CD total as well. If we do it for the next one, what's going to happen? So this is a Reynolds number of 10, and it's 1.5. So it's not quite reduced. It should be 1.3, right? If it's going down by an order of magnitude each time. So it's not quite doing that. So now it's here, and this is 1. So it's actually a bit higher. It's almost linear, I guess you could make a case. If you come down another order of magnitude, then we end up with this, which is 0.1. Instead of being 0.13, now it's 0.3, so it's double what it should be otherwise. And so you get the picture, is that this is basically flattening out. This is 1, this would be 10 to the 0, 10 to the minus 1, rather. So 0.3 would be about here. And as we go down one more, again, this is the last one we could do before it would blow up with these eddies in the downstream location, and it's only a third of that, so it's 0.1. And so you get the picture anyway. This is now the total drag that's occurring, and you see two regimes, right? You see this linear regime, which occurs up to a Reynolds number of about 10 to 0 or 10 to 1 in this particular case. And then you have a number which is not quite horizontal, but a much lower slope. And so that's just the mechanism of doing this. And so what's happening in this particular case is that now the influence of the viscous drag, this is linear with viscosity, so each time you change viscosity by an order of magnitude, this force goes down by an order of magnitude. So as we reduce the viscosity by an order of magnitude, this force goes down by the order of magnitude. This is saying that in this regime, this is viscous dominated, which is what we said before. When we get over this regime, all of a sudden it's not related to viscosity at all, because we can change viscosity as much as we like, and this stays roughly constant. And the reason it stays roughly constant is now that there's no longer this viscous influence anymore, so I suppose we could say this is viscosity independent. And it's due to pressure drag. And we could, if we wanted to and we had time, we could actually look at separating those things out. Actually, we could do it. Maybe we have time to do that. Let's look at that.
2 more seconds.
So the other thing this allows us to do, we've basically shown that, is that the other thing that we can show is that we could show what the viscous forces per area would be. So this is just the viscous component. So we'd imagine that if we looked at the very lowest Reynolds number, the highest viscosity, that force should be pretty close to the magnitude that we got from the total drag, right? And that was about 1,300 newtons. So it's close to that. It's about 1,000, right? So it's maybe 70% of the drag is due to that. Oops, can keep it. If we look at the case where we have it at 0.01, we would expect that the viscous force per unit area should be pretty small compared to the other one. Hopefully that's the case. What was our total drag that we had in that particular case? Does anyone remember? So the viscous drag is 0.03, and I guess the amount before, this was the other one, right? So it's actually, the total drag was 0.1. So 0.3 is maybe 40% of that. So the viscous drag, instead of being 70%, now is only 30% of the total drag. As we go up to progressively higher and higher Reynolds numbers, then the influence of the fluid pressure drag will completely dominate behavior, and therefore we get this behavior which is exactly this.
Great. Enough. All right, so you see exactly what the point we're trying to make is that the same calculations that we just did with a known solution for pressure and shear stresses on the system, you can get that information just as easily from a numerical model that defines that. Or you could measure those things in a wind tunnel as well and use them. And that gives you an ability to be able to calculate magnitudes of drag. So the most important things are that you saw maybe in that picture of the airfoil is that as we change the viscosity, which is changing the viscosity is really a proxy for keeping the viscosity the same and changing the velocity, right? As you get higher and higher Reynolds numbers in the same fluid, it just means you're increasing the velocity because of the reciprocal dependence, I guess, of those parameters. And so it comes back to our portion of wanting, if we're doing model studies, having the geometry right, having the kinematics correct. It's kind of epitomized here that as you increase the velocity from a low Reynolds number to a higher Reynolds number to an even higher Reynolds number, the geometry of the flow changes, and therefore you have to do your experiments or create your models at the right Reynolds number, and then, only then, can you use that to calculate the right forces that are on the system. And the two critical properties that you could get, and you could get it from Buckingham pi theory just as easily as what we've done here, is to figure out what these controlling parameters are. And if you do it for something like a sphere that has a sectional area, a flow velocity, a density of the fluid, and the viscosity, which kind of includes all the components of behavior, clearly pressure drag is a function of density. If you double the density, then you double the pressure drag at any given velocity because you have more mass per unit volume. And viscosity, which defines the shear drag, the viscous drag. So if you do that, use Buckingham pi for these, you get one parameter, which is the Reynolds number, which defines your kinematic similitude, and another parameter which gives you the magnitude of the force that you have to apply in the system as a function of an area, where these two components together is really the same as a pressure. Pressure, rho over v squared, is Euler number. And so that's how they fit. And so really the issue in what we're dealing with is being able to figure out exactly what the magnitude of these coefficients of lift or drag are. They're related to each other. And in figuring out the magnitudes exactly of what the forces are that are applied on the structure, along with an appropriate area. And the area has to be an appropriate area to the system. So if you're looking at a wing and you're trying to figure out what the lift is on that wing, probably the appropriate area is the area, the planiform area of that wing, rather than the frontal area along the leading edge, which would be probably more appropriate if you're calculating the drag. So you have to choose the properties appropriately, and we can define exactly what these would be. We did an example of this. This kind of really says, in microcosm, makes the point exactly of what was happening in these figures. And at low Reynolds numbers for the airfoil we looked at, as you went away from the wing, we got it to 1.6 times the external velocity. It's because it was constrained within a box in a tunnel. And so the same volumetric flow had to go in this smaller region here than it did before. If it was extended to infinity, then this value here wouldn't be 1.6, it would be 1. But if you have viscous flow, then you have this very slow change in velocity as you get far away from it. And it's this which is reflecting the importance of the viscous flow, because we know that from Newton's law of viscosity, the shear stress that's applied is equal to the viscosity times the change in velocity in the x direction as we go in the y direction. This is y. And so if this gradient is slowly changing and over a large length, that will give much more viscous resistance than it would do if, as we go across this boundary, this changes very sharply from zero velocity stuck here to the far field velocity much closer in. This is a much steeper gradient, but if it happens over an infinitesimally small length, then the product of the gradient and the length over which it occurs is much smaller than this effect here. And so when you get a boundary layer forming, the boundary layer tends up to be a very efficient way of being able to move this through the air. And you see these behaviors not just for a plate, as we saw here, but we've seen it for an airfoil in the example we did. You see it also in the case of a cylinder or a sphere going through the air. A sphere, of course, would be a ball, a golf ball or a baseball, where you get this separation on the backside, and it develops a fully turbulent flow and a wake on the backside here. And if you look at, we'll come back to this the next day, and actually I'll go into the first figure. Don't worry about this. This is the figure I'm looking for. So this is the relationship for either a cylinder going through air or a sphere going through air relative to Reynolds number and the drag that's applied on this. And I guess in the example that we did here, our threshold magnitude was at 10 to the 1, Reynolds number, defined in terms of a density, a velocity, and a characteristic dimension, which in our case was the length of the wing. Maybe it should be the frontal area of the wing, and the viscosity. And you see this laminar region, which is given by a number which is some coefficient divided by Reynolds number, inversely proportional to Reynolds number. And as you get in the turbulent regime, you move from a shear drag region, you can choose where that would be, to a pressure drag region occurring here. And it's exactly the same behavior that we've looked at in these. So the bottom line is that we can define these regimes which are laminar and turbulent. There are different dependencies in each of these in terms of the role of shear drag versus pressure drag in different parts. And ultimately, this affects the calculations that we will do to be able to look at the things we'd like to calculate. One would be the magnitude of the forces that are applied to a structure, lift or drag, which you could imagine if you have a wing that's going through the air at a certain velocity and you know the drag force which is applied, the product of the drag force times the velocity gives you the power that you have to push through. Or the alternative would be that we might want to use force balance to be able to calculate the terminal velocity at which you can move. And the calculations to do that we'll deal with next time, but we have to do a slightly different calculation if we're in this viscous regime versus if we're in this pressure-dominated regime, and they come out differently. And so we'll deal with that next time. So right on time. All right? Amazing. So I said I'd never subject you to it, but hey, I lied.